Maybe just a very quick recap, not many questions, we'll just quick recap a few questions and then come back to the photoelectric effect. If you can find that worksheet with you guys, yeah. Just few questions. If you guys started working on it, that would be great already. Or you just woke up, then it's not much can expect. Okay. I'll start with question 1. Or you guys want to give it a quick try? Hey, Vinura, so those questions including Young's double slit experiment as well?
Yeah.
Okay, so that means you've done pretty much. Okay, S1, S2, the question they're saying, so the wavelength is given. .625 nanometers. People who are just joining in, we're just going through a few questions, not every single question. Just few questions just to start, and then you guys can continue the rest of the question, hopefully. Bit of waves. I know that some of you guys finished the SAC. That doesn't matter. Just do a very quick try, and then we'll start photoelectric effect. Okay. So the question saying that, so the point C is at the center. So point C is at the center of the pattern A, and point A is located 2.5 further from slit 1 than slit 2. They're talking about path difference. So basically they're talking about S1A minus S2A as 2.5 micrometers. So they're asking, starting from point C and move directly towards point A, how many dark bands would be crossing? So if I want to find which bright band at point A or which dark band at point A, the best thing to do is divide the path difference by wavelength. That will give you the n value. If n is a whole number, then you can work it out. In our case, this is 2.5 micrometers, -6, 625 nanometers, -9. It's 4. N equals 4 means that's the 4th maximum. That means that point should be the 4th maximum. Or 4th antinodal point. That means you have to start counting from 1. You don't count the center one. 1, 2, 3. That's the 4th one. So that means you are passing 1, 2, 3, 4 dark bands. You pass in 4 dark bands in between. So the answer is simply, question is, fourth maxima. Therefore, so there are 4 dark bands between C and A. When you're moving, so these are the black dots are the bright bands. You start counting from 1, 2, 3, 4. You can see 4 dark spots. 1, 2, 3, 4. 4 dark spots in between. Use the appropriate physics principle to explain the existence of dark bands. Dark bands are formed by destructive interference. Destructive interference, this occurs when path difference becomes n minus half lambda. We can say where n equals 1, 2, 3, and so on. We can say it's a nodal point. Crest overlap with the trough. Okay. Question 3. Question 3. Adjustments are made to the experimental setup, which leads to a narrower pattern of dark and light bands. So which one or more of the following have occurred? Narrower means we're looking for the delta, the fringe spacing. Fringe spacing is if I get a series of bands, this is a bright one and a dark one and bright one and a dark one and so on. So this is what we call the fringe spacing. Distance between 2 antinodes or 2 nodes. If you want to bring the fringe spacing closer, so if I want to make it delta x to be smaller, you have to either make L smaller, lambda smaller, or D bigger. Because when you're increasing the D, it's trying to maintain the same path difference. So that means the pattern should come down. Okay, so to reduce, so this is your spectrum. Your wavelengths will be increasing that way. If I want to go, they're using, I don't know what light they're using. If they're using red, I can use any other colors to reduce the lambda. So the answers are, the laser was changed from red to green, that's okay, because red to green is here, it's a shorter wavelength. A is fine. The pair of slits are moved close together. That means if you decrease D, your delta X will be increasing. That's not good. The screen is moved closer. That's fine as well. You're reducing L. The intensity of the light, that's not relevant. It will increase the brightness of individual pattern, but the pattern will not stretch out or get closer. So there is no change on that. So A and C. Next question. Over the last few centuries, so this is like a one explanation question they can ask you all the time. There were two competing models, the particle model and the wave model. Because Newton's particle model was very strong, because he was quite famous. So therefore the particle model was there for centuries, although there were quite weaknesses. The particle model. That's where, if we heard about the story about Robert Hooke's and Newton's fight at that time, because Robert Hooke was supporting the wave model by looking at the diffraction and interference. And like a soap film, if you look at a soap film, like you produced by soap bubble, you can see the interference effects. So he was observing that. He was saying this can be happening on waves. But then Newton published his book, I think Optica. So then there was a controversy. Okay, so question one. Optics. So over the last few centuries, scientists have proposed two conflicting models, explain the nature of the light, wave model. Conflict the model, explain the nature of light, wave model, particle model. Name historical experiment supports. Name historical model supports the wave model of light. So the wave model was Young's double slit experiment. As the Young's double slit experiment. And demonstrated interference of light. Don't talk about diffraction. Demonstrated interference of light. So since interference is a unique property of light, he concluded that light has wave properties. Now, you guys, when you get a question like they're talking about wave model and the particle model, you have to mention why his experiment did not support particle model. Otherwise, you will not get the full marks. So you have to mention. So if the light, so particle model predicted two bright bands. On the screen, and essentially a dark band at the center. But that did not happen. So you had to mention about the particle model, why particle model failed in this experiment. Otherwise, you will not get the full marks. Because now there's a common question. Can't remember, I went through this kind of question last week. Maybe I won't do this question. I'll tell you like a general question. You guys give it a try at that question. Example. This is point P. So it's the second bright band from the center. So the path difference S2P minus S1P, say 1150 nanometers. Okay. Find lambda. So the next, that's the first part of the question. Now change the wavelength of light. And observe that the new wavelength produces the second dark band. At P. Find the new wavelength. So this is one of the typical questions sometimes you see in the exam. So they're giving us one scenario, finding the wavelength, and they change the wavelength, and then talking about a change in the pattern on the screen at the same spot, and ask you to find the new wavelength. Have you guys seen any of your SAC this kind of question, Lohit, Vinura? They're mixing up wavelengths. Okay, there is an answer there. Okay, you got the answer, Akshat, already? That's for the first part. Yeah, first part is fine because this is second maxima. Therefore, this is equal to 2 lambda. So your lambda is equal to 1150 divided by 2. 575 nanometers. Okay, that's the first part. The second part, yeah. 1150 divided by 2. That's good. You can see that the fringe pattern, they're getting spread out. Because your second dark here is moving here, means this pattern is spreading out. You have to see a longer wavelength. I think Akshat's answer is correct. Yeah, I think this other's answer is correct. So it's 1150 is equal to 1.5. divide by 1.5. Yep, 767. That's correct. Okay. So at same P, at the same position on the screen, the path difference remain constant. Path difference remain constant. So therefore, you can say second dark band means PD is equal to 1.5 lambda. Let's say lambda 2. So you can say 1.5 lambda 2 is equal to 1150. Okay. So you should get 766 or 767. 767, I think. 767 nanometers. That makes sense, guys? Yeah, everyone? Can you guys try the similar question, very similar question, question 7? Tell me what answer you guys getting. Any question, guys, about it? Do we need to know the wavelength of the, not the colors, individual colors? I would just maybe just put in your cheat sheet as a spectrum, electromagnetic spectrum, but you need to have a feel for it. We know that visible region is about 350 to like 700, and roughly about what wavelengths are. Okay, but they're not expecting. You just put a value in your cheat sheet. Okay. So give it a try, question 7 on this worksheet, guys. That one. And tell me the answer. Similar question. It's in page 3. Page 3 of this worksheet. That's it. The one that we started just before. Example 7. Anyone got any question about this previous question? Everyone clear with this? Because we're looking at the same spot, path difference should be the same. Hey, do you guys want a hard copy of wave prevision booklet? I know some people finished the exam. Anyone need a hard copy? If you need hard copy, tell me, I can print it out. Okay, so you need to come and unfortunately come and pick it up from our home. Yeah, maybe I'll print it out this week. I'll let you guys know. The next question is, you guys all remember this, a free end and fixed end. The resulting one would be going in the same direction after the reflection. Fixed end, it's going to invert back. So you have to explain how this happens. So you need to mention about how the forces are acting. In the first case, when you reach to the edge, there is a force acting on the ring, lifting up. Then the tension, vertical downward component of the tension pulling the ring back, and then convert the energy back to the rope. But in this case, there's a force exerts on the pole. The pole is exerting a force down. Action-reaction forces here. Just scribble that answer very quickly and then. Oh yeah, what's the answer you guys getting for the previous question? Yeah, that's correct. That's correct, 303. That's correct, 303 nanometers. The previous question. Okay, this one. Two parallel slits are illuminated by light composed of two different wavelengths. One of which is 486. The light whose wavelength is known produces its dark fringe at the same place. So it's a dark fringe, the third dark one. Unknown wavelength produces the fourth bright. Lambda 2. So you basically saying path difference should be the same. Therefore, I can say third dark means 2.5. Hey guys, when you say third dark, it's always 0.5 less. 2.5 lambda 1 is equal to fourth bright lambda 2. And solve for lambda 2. This is for 3 or 4 nanometers. Okay. Next question, just scribble that answer. So the tension without any inversion. There is no inverting. And then the other one, the fixed end. Okay, that will travel in the opposite direction. So only thing that you might have this kind of question more now this year because they have taken off chunk of the other Snell's law. Polarization, dispersion, Doppler effects. Therefore, you might have these kind of more questions. Okay. Maybe we'll move on. There will be a bit of a diagram. I think I'll let you guys try drawing. They bring together and look at the resultant and then draw it. Hey guys, how far you guys remember these kind of questions? Two speakers facing each other. The two speakers at a frequency of say 650 Hertz. The speed of sound is say 340 meters per second. A student is walking from A towards B. A towards B and stopped at second quiet point or minima. Second node. Find how far he is from A. Okay, you try. So I'm just picking out the common questions that you're coming in and to see how far you guys remember this stuff. Lakshya, you remember how to do these kind of questions? Yeah, give it a try. The things that you guys need to remember when you have two speakers facing each other, the two ends close to the speakers, they're acting like antinodes. So you're standing where the center is always antinode because its path difference equal to 0. Always construct interference at the center. Near the speakers, they're acting like two free ends. I just drawn something for you guys to make it easier. Okay, so let's see whether you guys are getting the answer. So what's the expected answer? Yep, anyone got the answer yet? Dylan, what's happening to Dylan? What's happening, Dylan? Okay. Yep, Hassan, I think you're correct. Yep, you're right, Hassan. Not 0.78, no. .78, I think that's the wavelength, right? Okay, guys, just to save time. So he's walking from the end towards B. Remember, this is antinode. Antinode to node position, that's a quarter wavelength. Here, that's a quarter. That's lambda on 4. And from a node to another node, that's a second quiet point. I said second quiet point, second node. That to that, that's a half a wavelength. Node to node, that's a half a wavelength. The total distance is walking. That's a 3/4 of the wavelength. And find the wavelength, V equals F lambda. Okay, so your lambda is going to be V on F. The V was 340, F was 650. I think, yeah, Tisara got the answer. .340 divided by 650. So 0.52. And you get the 3/4 of that. That's where 0.39 comes in. Okay, remember guys, people didn't know how to do this question when they first gave this question a couple of years ago. Okay, I think a few people did it. towards A and stopped at the, let's say, a second quiet point. Find the distance. Find the distance from A. So she's walking from the center. The best thing to draw like a standing wave at this for your easiness to work the question, just draw a standing wave at the center, always antinode. So you can start counting. Sakshat got the answer. Is that for the previous one or oh, maybe the previous one, Akshat, yeah. 0.39, yeah, that's for the previous one. Naveen, that's correct. Can you get that question quickly get through? Now from the center, he's walking from the center. Hey, can you guys please finish these questions here? Because I really don't want to spend time going through these questions. If you guys really ask me, I can go through it. But I'm just begging you guys, just finish it off. I'll put the answers as well. Okay. All right. That's 6 meters. That's A. So she's walking from the center. Center is always antinode. She's starting from there and then stopping at the second antinode. That's the first one. That's the second one. That's where she's going to stand now. We're trying to find that length. The second node from the center. No, second node from the center. If she's standing at the center, the second quiet from the center. So when she is walking from center towards A, so she's stopping at the second quiet point. She's walking from the center towards A and stopped at the second quiet point. Yeah. But we're asking the distance from A. Yeah, 2.65 seems reasonable. No. Oh, yeah, maybe that's reasonable. Yes, that's reasonable. The first thing is find your lambda. The lambda is V on F. .47. Again, you can see from here to here, antinode to antinode, that's half a wavelength. And antinode to nodal point, that's a quarter. Again, she is traveling 3/4 of a wavelength. Okay, the total distance from the center towards A. Lambda by 2 plus lambda by 4. Okay. So your lambda is that. That's from the center. That's 0.35 from the center. 3535 meters from the center. So the distance from A, so it's to the center, guys, is 3 meters halfway through. So 3 take away that value. So 2.65. Okay. You guys okay to handle those ones? Both in fixed string at a frequency 250 hertz. So V is equal to maybe 150 along the string. Find L. Very simple question. The second part of it. Anyone got the number? Okay. Yeah, 2.465 previous question is good. This is world easiest question. Yeah. That's good. Tisra, Akshat, yeah. Okay, so you can find the wavelength. This is half a wavelength. Okay, so your lambda is equal to, so 150 divided by 250, I think 0.6. And 3 meters. Now the students are changing the length. Find the new length. Oh, everyone having internet issues today. What's going on? That Glen Waverley area, that particular provider. Everyone watching Netflix, maybe. The third harmonic is 3 loops. Yeah, Pasan, Tisara, Lakshri, Akshat. Yeah, it's all good. So that's, we can see 3 halves there. Because we haven't changed the frequency, the wavelength should be staying the same. Frequency stayed the same, the lambda is constant. Lambda is 0.6 meters. .9 meters. Okay. Another one more question. That's it. We'll just move on. Now you guys need to finish the other questions at home. That was a question. This was a question on the other booklet. I don't know how many people did that. Student is walking from very far distance, relatively far distance, towards these 2 speakers, but she's walking along this lower speaker. Now first, like so far she's having equal sound intensity, and suddenly she's experiencing first quiet point here. She's experiencing first quiet point while she's walking towards A. Okay, so we ask you to find x. The lambda is 2 meters. Hey, what's going on today? Everyone's sort of getting kicked out. Hey, your reception is pretty bad, or what's going on? Internet reception? Is that okay? I think it looks like the problem is happening in the Glen Waverley side, yeah? Glen Waverley Mount. I don't know whether it's a one provider. Yes. Oh, they announced a problem. Okay. Yeah. The Shani rang me saying that she can't connect at all. Telstra, okay. Okay. That's not good. Using mobile data. Damn. All right. Okay, free lesson then. No charge. Okay, do the questions. Okay. Find x. So you don't need to pay for today. Find x. Okay. The first one to get the answer, maybe get this lesson and next lesson going to be free, but only one person. Get the answer for x. Okay. Lujit got it. Lujit got the answer. Okay, Lujit, you don't need to pay for this lesson and next lesson. And your brother got it, but I think brother is a little bit behind. Hey guys, first point means the path difference is equal to 0.5 lambda. 0.5 lambda. So 0.5 lambda means path difference is equal to 1 meter. That's 1 meter. If that is x, that should be x plus 1. Okay, if that is x, that should be x plus 1. All right, so you can say, if you can use Pythagoras, x squared plus 3 squared is equal to x plus 1 squared. Okay, so that's x squared plus 9, x squared plus 2x plus 1, x equal to 4 meters. Okay. So the path difference is equal to 1 meter because 0.5 lambda, first point means 0.5 lambda. That's 1 meter. Okay. All right, I think we had to move on. Please do questions, guys. Please do this question. If you collect all the wave questions I gave, that's enough pretty much for your SAC preparation, people who haven't done the SAC. But I'll give you more. But I hope you guys can capitalize on these questions. Okay. Now the next section is looking at light and matter. So particle properties of light. So this problem came in like the beginning of 20th century, 1900s. Remember Young's double slit experiment was like 1800, nearly 100 years later. Okay, so now everyone clearly convinced Light is a wave because it produces interference as well as diffraction. Only waves can produce those qualities, nothing else. So everyone convinced light is a wave. Confirm. The wave nature of light. Wave nature of light. So if the light is a wave, its energy should be related to the intensity or the amplitude. Intensity of light. Or amplitude squared. Intensity of light. Brighter the light, and you think that higher the energy. If I can draw a light wave as a function of time, it would be something like that. That's the amplitude. The higher the intensity, higher the amplitude. All right, so with that in mind, like people are just convinced that there's nothing else, light is a wave. Max Planck, he was doing some experiment on the side. This later on, he kind of started to observe some funny things. He was observing the emission spectrum with the absorption spectrum, emission spectrum. People reasonably familiar with it. That's a light coming out. Emission spectrum of hot objects. Emission spectrum of hot objects. He was expecting the light wave should be coming out. It has to have a, like, before that, they knew that white light has a particles, like a combination of different colors in Newton's time. That's why Newton was sort of very strong advocate of the particle property of light at that time. He was thinking it's a mixture of particles together. And he was thinking when these particles enters into a medium like glass or water, there is a force, interactive force between these particles, pulling it towards the towards inside the material. But according to his theory, the speed light should be speed up in a denser medium. Okay, when he was looking at this spectrum of hot objects, so it is red hot. He was saying that the light coming out from these hot objects, the hot red objects, are not continuous. Spectrum wasn't continuous. Spectrum was not continuous, or it was rather discrete. discrete. So he wasn't sure why it's not getting a continuous spectrum of light. But he managed to come up with saying that according to his belief, because when you heat up these particles or electrons inside, electrons start to oscillate, yeah, vibrate. This is inside the material. When you heat it up, start to oscillate. Now, electron has to lose some energy, and when it's giving off, as light, electron has to lose some energy when it's giving off that as light. He thought the energy of the electrons, because they have some sort of energy, these energies were quantized. Energies of the electrons were quantized. That means they are not continuous. Suggested that energy of electrons were related to the frequency of the vibration. Now, maybe I'll write it somewhere. Maybe I'll write it here. This is inside, okay? This is hot object. This is what is black body radiation theory. Planck suggested that energy of the electrons objects are quantized. That means they are not continuous. They're like a packets. They are quantized or like energy packets. So the energies, these energies are related to the frequency of the vibration. So that means, so some electron maybe have a E1 amount of energy. So he was saying it might have like a 5 times the frequency. It's maybe related to the 5 times the frequency, one of them. Another one, or maybe just say E5, or maybe say E1. No, just say, okay, just say E5, 5F. Another one maybe 3F, and so on. 2F. So each electron has a certain amount of energy. So what he was saying, he was linking that with some sort of a constant. That's what we call a Planck constant. Hey guys, now he was saying, let's say this guy is losing some energy. If he's losing energy, he can lose one quantity, one packet. You got 5 packets inside. He lose 1 packet means he's going back to 4F and giving off 1F here. So the light coming out is proportional to the frequency, just one frequency. Okay, that one has like, these are quantized quantity, like a packet, like multiple of amount. Okay, so therefore he started to say the energy of these photons or light coming out he said is equals HF. H is the Planck's constant. You guys see that part? Yes. H is the Planck's. It's a constant he introduced by seeing by experimental observation. That value is 6.63 times 10 to the power negative 34. It's joules second. You guys need to know that number all the time. Joules second equals HF. Now we have another unit. We converted 1 electron volt is 1.6 times 10 to the power negative 19 joules. If we convert this Planck's constant into electron volts, if you divide by that number, you get 4.14 negative 15. Remember the two different units, electron volt second and joule second. So that's the back end story. And people knew that the C equals F lambda because the wave nature, they connect that back to here, E equals epsilon lambda as well. Okay, you need those equations later on. C is the speed of light, lambda is the, because this is coming from the connection, the wave behavior of light. But they say the Planck, although he observed this funny discrete behavior, he was expecting like a continuous spectrum because its energy is just light coming like a continuous intense light. He wasn't going in detail, but he didn't criticize anything to do against the wave behavior. That's why they're not recognizing Planck's work for the particle behavior of light, but giving more prominence to the Philippe Lenard's experiment plus Einstein. Because Einstein was critical, saying that wave model can't apply here straight away. But the Max Planck did quite a bit of work, giving that background information. Okay, that's there. Now the biggest failure of wave model came during an experiment. So take home message, keep in mind, if the light is a wave, energy should be depends on the intensity. If in some experiment you can see some funny results where the energy does not depends on the intensity, then you have to question what's going on with this model. Now, the Hertz, this frequency guy, was performing some experiment to generate electromagnetic waves. This is just for the story, just to continuation of the story, but Hertz work, no one going to ask in the question for the exam, but it's nice for the story to be that. Electromagnetic waves. Let's be simplified, say the experiment. He was shining different light. So say he's shining ultraviolet into a metal. It's a metal surface. well-polished metal surface. So what he was finding is whenever you shine the light, you can see it building up a positive polarity here. It becoming positively charged, the surface. If that is positively charged, means you're removing some electrons. Initially found that the metal was positively charged, that means you're lifting some electron out. Indicating liberation of electrons. Or ejection of electrons. From the metal. And also, he realized that so when you do conduct the experiment, maybe in a dark room kind of scenario, you can see the sparks coming out. Sparks are electrons interacting with air molecules. Sparks emitted from the metal. The sparks are electrons, keep in mind. Sparks are electrons interacting with the air molecules. Hey guys, now the interesting thing was when he was shining, increasing the intensity of a certain light, he was saying that the sparks are jumping the same distance. Then when he was changing the frequency, say blue light to ultraviolet, he observed that sparks are jumping further, indicating sparks get more energy with high frequency light. Ejected electrons. Increasing frequency of light. But not with the increasing intensity. So this is more kinetic energy here. It's jumping further. That's where the breaking point, because if the wave model is correct, If you increase the intensity, that means you give him more energy. If the electron jumps further, that makes sense. Okay. So that was against the Wave model's prediction. So he reported his observations. This is something funny going on, but I have no idea. But I am not interested to pursue this observation any further. Anyone interested, they can follow this one up. That's what he basically said. Okay, so these fine results coming up. This is something unusual, but I'm not interested to continue any further work. If anyone else interested, just follow this one. That's exactly what Philippe Lenard did. Now, this Philippe Lenard's experiment, you guys need to know for the exam. You probably don't need the guy's name, but you really need to know. That's 300% sure your question will be there in the exam. Okay. Double P plus Lenard. The aim of the experiment was to investigate what the Hertz was suggesting and maybe a bit of Planck's suggestion as well. So he wanted to change the intensity and see how far the electrons are jumping, or whether the electrons gaining more kinetic energy with intensity or with the frequency. Now, to investigate, depends on the frequency or depends on intensity. Okay, guys, another note saying that the ejection of electron So Einstein got the Nobel Prize for photoelectric effect, not for relativity. When they nominated him for the first time, they said his contribution wasn't enough. They took another year to consider. And they say photoelectric effect and other contribution to physics or something. They just changed the name when they're awarding the. Okay. Now, photoelectric effect, now keep in mind, there are numerous ways electromagnetic waves can interact with atoms. Photoelectric effect generally happen the electromagnetic waves with low energy. So when you go to get X-ray for your broken bone, there are photoelectric effect happening even in your atoms. Okay. When people are getting treatment for the cancer, for the superficial cancers, like skin cancers, most of the interaction is photoelectric. But when you're trying to get high energy electromagnetic waves, so there is another way of interaction that's called Compton effect. We're going to touch on Compton effect, not going very far. And if the energy is too high, then there is a pair production happening. That means a photon comes in, convert into electron and a positron. Okay, and there's a third interaction can happen as well. That's called a triplet production. So we just touching on the first type, photoelectric effect. Keep in mind. Now, he set up the experiment. The aim of first experiment, we'll just make it at first experiment. This is Philip Lenard's experiment. He kept the frequency of light constant. You can't change too many variables. So he kept frequency constant. And change the intensity of the light. Hey guys, need to understand the bigger picture here. So if you have a metal, let's say there is electron here, you supply energy externally from a light source. Electron is ejecting after receiving that energy, purely kinetic energy. If I want to measure this energy, what kind of a setup I need? Think about people just finish your EPI or maybe put into the experimental hat. I want to measure, okay, maybe measure how many electrons are ejecting from a metal. What's the easiest way to measure the number of electrons coming out of a surface? What is the word after? Depends on frequency. Depends on frequency or depends on intensity? Dependent, I don't know. Okay. Charge, okay. Charge, yes. Go, give me a bit more. What's the word? Yep, current would be a better choice. Yes, I want to measure the current. But can I set up an experiment, say, I don't know, what something else need to come? So, okay, that's my metal. I'm shining light. How do I control frequency, guys? How do I keep the frequency constant? How do I keep my frequency constant? Okay, maybe I'm using white light to start with. I want to have a constant frequency. That's the metal. White light, or maybe some electromagnetic wave. I want to select a particular frequency. I can put a filter, a colored filter. Then I know that only if it is blue filter, only blue light coming through. Yes. And the light shining onto this metal, electrons are ejecting, they have kinetic energy. I need to put some sort of a collector to collect that. Still there's some issue with this. Yes, single wavelength light, yes. I can use a single wavelength light, or maybe use a colored light and put a filter. Either way should work. What's the problem with this kind of a setup still? Electrons are ejecting, that's fine. Why the sparks? Because electrons are interacting with the air molecules and heating up and losing energy. How to avoid that? I need a vacuum. I need a vacuum. Okay, that's a vacuum. And then I can put this one into a circuit. And then this current is measured. So this is electric field. I'm applying an electric field. This is the cathode, or maybe just the emitter, and that's a collector. Okay, say anode. That's the emitter. Cathode. That whatever the side that emits electron, we call a cathode. But don't mix up with your cations and anions in your chemistry. And this is like a very sensitive ammeter. I initially made this one to be positive. Electrons can accelerate. That's the electric field here. I can change that voltage. It's a variable voltage power supply. Now the electrons gain energy because of the light shining onto it. Gain the energy. They jump into the collector. Jumping into the collector. And then he started plotting graphs. We measure the current. Maybe these are microamps. And that's the voltage. This is the low intensity light. Low intensity light when the voltage, this is the accelerating voltage. What they found was even if you have a small voltage, positive accelerating voltage enough to pull all the electrons to the collector. But when that accelerating voltage is getting zero, you can see it dropping off some current. Because the reason is there is no increase in current here. There's a limited number of electrons. These electrons, ejected electrons, depends on the energy they received. And we're helping them out to reach the collector. That's why there is no further increasing in current. You have X amount of electron there per unit time. So you're pulling them out. Remember, the current is the rate of charges collecting in the circuit per unit time. The most interesting part was he wanted to now apply a reverse potential. He wanted to stop the electrons. rather than helping them out. Okay, before we talked about reverse potential, can I get your attention, guys? This is the metal surface. Think about this simple model here. Let's say electrons are buried at different levels. Some of the electrons easy to ionize, take it out. Some of them are difficult. Okay, some sort of we need energy supply to liberate them. Let's say this is the least bound electron. We're talking about this least bound electron lots of time. Okay, let's, for argument's sake, say you have the light source, you're shining light. So the light may be giving, say, 50 electron volts of energy. Just simple argument. 50 electron volts of energy. We don't know yet the energy is coming as a particle or as a wave. Let's say that energy is coming as 50. The least bound electron, it may be required about 5 electron volts just to come out. The guy just next door, maybe he needs we need to spend about 10 EV to come out. This guy maybe needed 20 EV. This guy maybe, don't know, 30 EV, and so on. But this is the least bound electron. When that comes out, when that liberated and comes out, how much? This is purely kinetic energy. You're receiving 50, you had to spend 5 to get out. It will have 45 electron volts of kinetic energy. This is purely kinetic energy. Just to check whether you guys are paying attention to my explanation, if I ask you, if I want to, so these electrons are coming out, remember, from the metal, they're coming out. They have range of energies. If I want to stop by applying a reverse electric field, but I'm changing that electric field gradually until stop the most energetic one. Which one I would stop at the very end? When I'm shining the light onto the metal, electrons are coming out with range of energies. Okay, I'm going to crank my, now you guys need to draw this circuit with the reverse potential as well, unfortunately, but that's what you normally get mostly in the exam question, the reverse one. That become positive now. Because the reverse potential, you guys like the word, sometimes called retarding potential. Okay, which is easy to remember. Yes, so it's called reverse potential. You guys need to draw the previous one as well, just to indicate how that works. That's the accelerating. Now this is the reverse or retarding potential. Because this guy wants to do some work. Remember, the work is going to be given by EV equation. It's applying a reverse potential now until stop the most energetic one. No one answered that my question. That means I just feel sad. That means no one understood what I was talking about before, maybe. Go back to my simple model. I am giving 50 eV. Electrons are buried at different levels from the metal surface. Some electrons need more energy to come out. We are interested on this guy, the least bound electron, because that's the electron need least amount of energy to come out. If I give 50, we have to spend 5. We're losing that 5. Okay, we're losing that 5 and comes out. Okay, and the other ones, when they're coming out, they have only 40. This guy has only 20. This guy 30. This least bound electron will have the highest kinetic energy. Now, I am going to stop preferentially these electrons by applying a reverse potential. Okay, the aim of the reverse potential is gradually stop the electrons reaching the collector. Reversed, okay. Reaching the collector. Okay, until all the electrons are reaching the collector. Keep in mind, the final electron that will be stopped that's the highest kinetic energy. Because understood what I was saying, you're reversing it and gradually cranking up the reverse potential until your photocurrent becomes 0. This is called photocurrent because the current produced by the light. Until photocurrent becomes 0. Okay, once that happened, then he realized that it's coming down, coming down, coming down, coming down. Stop. And this is the retarding potential. This way accelerating, this way reverse potential. We take only the magnitude, we don't put the negative value. You're doing work against the motion of the electron. This is called stopping voltage. This is very important one. This is called stopping voltage or cutoff voltage. It is the minimum voltage required to stop the most energetic electron. I had to write somewhere Vs stopping voltage. That's the minimum reverse voltage. Most energetic electron. Now, there is a link between the kinetic energy, because this guy has the maximum kinetic energy, guys. So kinetic energy max, EK max, or KE max. So you can say that the kinetic energy maximum, because you're doing work against it, the charge of an electron, stopping voltage. EK max or KE max. That's another equation you guys need. E is the charge of an electron. Now, how far you guys are grasping this? Justin, what do you think? Okay. Now he increased the intensity. That's the high intensity light. Now wave model predicted that, okay, if I am giving higher intensity to the light, to the metal, you supply more energy. Then the least bound electron should be gaining more energy. So if I'm trying to stop that least bound electron, I need to apply a bigger reverse potential. That's what the wave model predicted. The wave model thought, okay, you need a bigger stopping voltage because I'm giving more energy. So the wave model was happy with that because you get more current now. It's kind of indicating giving more energy. But that wasn't expected. This is a high intensity light. High intensity. Doesn't matter low intensity or high intensity, they both have the same stopping voltage. That was puzzling. That was against the wave model prediction. according to wave model. Wave model predicted greater stopping voltage. Greater stopping voltage with high intensity light. Because it's assumed that more energy is given. However, that did not happen. So that was disappointing for the wave model. Wave model expected, okay, yes, I'm giving more intense light. That means more energy. Now remember guys, the way that the wave is supplying energy compared to a particle supplying energy. Think about tsunami. Tsunami is a massive wave, powerful wave, yes? When the wave comes in, it can destroy lots of people, lots of buildings, lots of property at one go. That energy can give one to many. That's how the wave is supplying energy, one to many. Now I want to hit people using cricket balls. People are a bit scattered. So I can hit one person at a time. So the way that the energy supplied by a particle is one to one. Wave, one to many. Okay, particle, one to one. Okay, keep in mind that's just like a little thing to remember. So they thought if I increase the high intensity, overall you're giving more energy to all the electrons. Even this guy, least bound guy, will get more energy. Therefore, I need to apply a bigger electric field to stop it. But that did not happen. Okay, maybe second experiment we'll talk about next week, but before we finish that, I'll just recap a few things. The energy of a light particle, we'll talk about particle more pronouncedly, more clearly once we get that model up. Energy is given by E equals HF. Okay, now you can write that as E equals Hc on lambda. Okay, Ek max is the maximum kinetic energy. This is related to the least bound electron, the one that's coming out. To stop that, I need to apply a larger voltage. That's the voltage making your photocurrent to be zero. If you crank your reverse voltage to Vs, if you're doing that experiment, you have to be very careful. Some schools, they have the setup. You can't just crank it to maximum the negative voltage, reverse voltage. Of course, your current will become zero, but that's not going to be your stopping voltage. You need to watch your current and slowly crank it, slowly crank it, slowly crank it. Now, 5 micrograms, 2 micrograms, 1 microgram, 0. Then you stop it, get the reading. That's how you work out your stopping voltage. If I crank it, yep, photocurrent is 0. My voltage was 15 volts, negative. But in fact, your stopping voltage could be 5. Yes, do you understand what I'm saying? If you crank it too much, yes, photocurrent is going to be 0. If you want to get that critical value, you need to go and do the experiment where it's load. There are simulations. There are simulations you can just change your reverse voltage and check how the current is changing. I would encourage you guys to give it a try. Okay, rather than I'm starting the second experiment, I'll ask you to calculate the energy. If the stopping voltage is 1.5, find the maximum speed. So we know that EK max is equal to EVS. This is half. We don't consider any relativistic effects. .5 and solve for V. Okay, meters per second. Joules and electron volts. So to find the energy, you can use E equals epsilon lambda. For joules, you can use 6.63, negative 34. Lambda is, you need to convert into meters. You get 442.19. You can convert directly into electron volts here as well. You basically divide it by 1.6, negative 19. So rule of thumb, your electron volts value should be like a small number, round number. In this case, I'm getting like 0.28 electron volts. The photoelectric effect, explaining the concept is a little bit of tiring. Maybe once you get that one passed through, I think it should be quite straightforward. As long as you get something out of it, that's the main thing. Okay. The next experiment is you keep the intensity constant, you change the frequency. Obviously, when they change the frequency, what they observed was the photocurrent stays the same. Here, stopping voltage change. Higher frequency gave higher stopping voltage. clearly indicating the energy received by the electron, something to do with the frequency of light rather than the intensity. Okay. Any question, guys? Yeah, that's the speed you get, 7.3 times 10 to the power. I can simplify that. 3.2 negative 19 times 1.5 divided by negative 31, square root of that. Yeah, you get 7.26 times 1, 2, 3, 4, 5, yeah? 10 to the power 5, 1, 2, 3, 4, 5. 7.26 times 10 to the power 5. That's what I got. Okay. All right. Any question, Praveen? Kishan, you there, Kishan? Yeah. All right. Okay. I'll let you guys go then. Tisara, any questions? Yeah, you guys don't need to pay for today's lesson. So put into the internet basket. Akshay, any questions? Hey, when is your next sack? That's I had to keep an eye on that. Suddenly you said your sack is tomorrow. Akshay, when is your sack? The last sack?
I don't know.
I think you guys having a kind of poster thing, yeah?
Oh yeah, we're doing that now.
Yeah, okay. All right. Okay, I'll let you guys go. Okay, bye guys.
Thank you.
Thanks, sir.
Thank you, sir.
Bye.
Cheers, sir.
Thanks, sir.
Bye.